Now, another type of comparison test is the limit comparison test. Whenever I don't say what type of comparison test I'm using, it is always the direct comparison test that I talked about in a previous video. But if I do say it, I can say that it's either the direct comparison or that it is the limit comparison test. And as the name implies, the limit comparison test requires you to calculate a limit. So this is the limit that you are going to calculate on the limit comparison test. Let me make this a tiny bit bigger. Whenever you're comparing two series and you can't clearly see which one is bigger than the other, but you sort of have an inkling, have an idea of what your series should compare to, then you can use the comparison test, the limit comparison test. So what is the deal of this? If you have two series, again, they have to have positive terms. So you can't really have a negative and a positive series. You need to have it, both of them being positive. Again, I'll talk about having series that are negative at times, how to deal with them. So assume they're both positive terms, both series of positive terms, and then have a n and b. And this time there is no certain direct order. You don't know for sure which one is the bigger one, but you know that if you take the limit of one divided by the other, then that equals c. What the test is saying, what the theorem is saying, is that that means that either both converge or both diverge. So the limit being equal to c and c non-zero just means that they're practically the same. So let's imagine, for example, just for illustration purposes, that the limit of an over bn when n goes to infinity is, I don't know, 3. Let's say it's 3. Just imagine it's 3. As long as it's not 0, the theorem will work. So, of course, the limit, this equation means that this fraction for very large n is very close to 3. So that means that for large n, a n over bn is approximately equal to 3, right? That's what a limit is. When you plug in the values that are closer and closer to what n is going to, you get something closer and closer to what the limit is. And so from this approximate inequality or equation here, you can move the bn over. You can see that the an's are approximately triple the bn's. Right? So what does that mean? So that means the following. If I'm adding the terms of an, I'd be adding a1 plus a2 plus dot 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 up to very large values. So let's actually give it numbers. Let's say I'm adding a1000 and a1001 and so on. Right? Because of this, because the an's are practically triple the bn's, for very large n values, this will be the same approximately as, sure, maybe the first a's don't exactly equal or compare very well, but this is going to be approximately triple the bn, b1000, right? Approximately. And then approximately triple the b1001 and so on. So if you ignore this for a while, just leave it be on its own, this is about triple the b1001, about triple the, b1000, and so on. So this is basically another sum, but now with b starting at 1000, with n starting at 1000. Okay? So, of course, this is finite because I'm stopping before a certain number of terms, right? There's only 999 numbers here. So in this parentheses, I have something that's finite. So it doesn't make a difference. And of course, if the bn's go to infinity, then triple them will also be infinity. And so adding a finite number will also be infinity. And so if the bn diverges, then this will also diverge. Okay? And likewise, the other way around, if this was already infinite to begin with, if I already knew that that was infinite, because I know this is finite, then for sure this has to be the infinite part, right? The bn's have to be infinite. Otherwise, if both are finite, there's no way that I'd get an infinite number when I add the two. So that kind of makes sense. The series are sort of tied together whenever I do the limit and I get the c non-zero. I did it with 3, but as long as it's not 0, everything's fine. If you do get 0, then everything times 0 here just goes away and you have a finite number and nothing helps you, okay? So just have to have a limit that equals 0 and, that does not equal 0, okay? And you should be fine. The series are tied together. Both diverge or both converge. Okay, let's use this in a few examples. I have an example that we did earlier, and an example we did with the direct comparison test. This one required us to do sort of out there a weird comparison, but this time it makes more sense. Looking at this, I can see that 1 over n cubed, n squared, if I ignore the minus 1, this is 1 over n squared. So when I look at it, I think, okay, this is essentially 1 over n squared, which should converge, right? But right now I don't know because this doesn't compare correctly to that. Just go watch the video from before and you'll see what I mean. What do I do then? I just divide the two series. For a, I say this. I say take bn to be 1 over n squared. We know this converges. And I'll start at 2 here because that's where my series starts. And it's a p series. Here, p equals 2. I always have to give my reasons. Always, always. Doesn't matter how obvious I think the reasons are. I have to give them. Now, what I do is I take the limit. Let's do an over bn. An is going to be this one. And the other is going to be this one. So let's solve this limit as normal, as if we were back in calculus 1. So n goes to infinity. Division of fractions, repeat the first fraction, multiply by the other one upside down. I get n squared over n times the square root of this. So on this square root, I'm going to factor n squared to get 1 minus 1 over n squared, like this. So do limit n goes to infinity. This n squared gets to come out of the root and is going to positive infinity, so everything's positive. And so this n that gets out of the root just becomes a single n that multiplies with the n that's already outside to make an n squared that I can then cancel with this. And so this is limit n goes to infinity, 1 over root 1 minus 1 over n squared. Let me move this down a bit, because then you can see that this is 1 over 1, which is 1, which is definitely not 0, which is great. And so because I knew the other one converged, this one converged, and the limit was 1, that means the series are approximately equal for large n values. They're tied together. So that means they both converge. And so I have to say that the given series converges, and I gotta say the name of the test I'm using, by the direct comparison test. Excuse me, not the direct, the limit comparison test. The direct was the one we did before. Okay. Stop, think about it, understand my reasoning. Let's solve the second example. See, same idea. I wish I could ignore this 5, right? because then that would be e to the power n, n e to the power n, which canceled becomes just 1 over n, which is the harmonic series, which diverges. And so I think that the series that I'm given diverges as well. Unfortunately, though, this side is bigger because you have a smaller denominator. Smaller denominator equals bigger fraction. And so, of course, this is bigger because this is infinite, right? So this may be infinite as well and maybe finite. So I don't know. The comparison that I get from direct comparison doesn't work very well. So when that happens, it's a good idea to use the limit comparison test. So I'm going to compare it to the harmonic. All this that I just wrote on the board in green is something that you can do in your scratch paper before you decide what to do. And then you see, like I did here, you erase it all and then pretend like you knew what was going to happen from the very beginning. So that's how mathematicians do things. So I'm going to do the same for B. I'm going to take my Bn to be e to the power n, 1 over n, right? That's the one that I think it compares to. This diverges because it's harmonic. And so if I take the limit of an over bn, when n goes to infinity, that will be e to the power n, e to the power n plus 5, all of that divided by 1 over n. All of that divided by 1 over n, with the bigger fraction being the bottom one. So I repeat the first fraction, multiply by the other one upside down. So I'll get n goes to infinity, n over, so e to the power n, e to the power n plus 5. I can factor out a whole, n e to the power n like this from the bottom, which will give me 1 plus 5 over n e to the power n. These cancel, and I get limit 1 over 1 plus 5 over e to the power n times e to the power n. And this goes to infinity, so this goes to 0. And so this again goes to 1. It didn't have to go to 1, it just happened to. As long as it goes to something non-zero, I'm fine. This diverges, which means the other one that I was given also diverged. So I can say, therefore, the other series, I'll say n e to the power n, e to the power n plus 5 diverges by the limit comparison test. There's a whole array of series that you can figure out now whether they converge or whether they diverge. And here's something that I'm going to show. For example, if you have something like this, this converges. You can try it yourself. I'm not going to solve it. And that's because of the integral test. Right? That's because of the integral test. So if you take this one now, let's say we say n to the power 5 over e to the power n. Will that converge? Knowing that the black one converges, will that one converge, or will that one diverge? You'd think that it converges, but the comparison isn't the correct one. You see, the blue one is bigger, and for it to converge by direct comparison, you'd need it to be smaller than the black one, which you know converges. So that doesn't quite work. You can try the limit comparison test. I'm going to do this. I'll take the one that I think is bigger. And I'll do... I think this one is smaller, actually, so I'll put it on the top. I'll do this. Divide the small one by the big one. And, of course, after all cancellations, this will be 0, right? This will be 0. And what does that mean? What does that mean? Are the two series tied together or not, right? It's hard to tell. So here's the idea. The limit comparison test does not apply because this is 0. And it explicitly asks you that the limit is a C non-zero. So here I can say that the limit comparison test does not apply. If you're on a test, on an exam, the correct thing to do is to either think of a different test or somehow use this limit that you figured out to try and understand what should happen. What things should you be thinking about? Maybe I'm going to save this for another day, but just pay attention here that this particular test does not apply here, even though, and I'm going to tell you this in a future video, this does converge, okay? So it is not an end-all be-all, but it does converge. There will be another test that will apply to the situation.